Hi again. So in this video, we're going to look at developing a model for two proportions. Okay, so before we get into the actual formula and conditions, I want to show you what happens when we have more than one thing that varies, okay? And this actually relates to one of the things I did when I worked for Saturn. So when you have more than one thing, like two proportions or two means, multiple things are varying, right? So this is called a tolerance stack in manufacturing. So whenever you're building a car or any kind of assembly, you have multiple parts, right? So here's the side view of what, like a blueprint of an assembly, where you have 1, 2, 3, 4 pieces that are being put together. And then over on the right side, you can see this is the total assembly with the parts all put together, right? So this is like a slice through, so you can see what it looks like with the little slice of each part as it's put together. Now, each part is going to vary, right, based on the manufacturing process. Like, let's say they're stamping a metal part. When you're stamping this sheet metal, the tool is going to wear, and so as the tool wears and it gets kind of smaller, then their parts can actually get larger. Same thing with holes. Let's say you're punching a hole in a part, then as the pin wears, it gets smaller, and the hole gets smaller, right? So things change over time. Also, if you have two different lines making the same thing, those tools might be slightly different. So wear and something breaks off, you repair the tool, maybe the pin is in a slightly different place. There's all kinds of things that happen in manufacturing where every single part is not exactly the same, okay? And yet you need to put them all together and build a car that works, right? And also build a car that looks decent. Doesn't look like it's gonna fall apart as it's coming off the line, right? So part of my job at Saturn was, this was called dimensional analysis or dimensional variation analysis, was there's this little notation or coding for how much each part can vary and still be able to make the assembly work, okay? And there's also different ones for hole positions and things like that. These are just some of the different types. Okay, so this case we have 4 things varying, but look over here in the assembly. Let's say we really want to know the space between these two things. So it's really the top and the bottom piece, and there's a gap right there. We want to know maybe there needs to be a certain gap for things to function. Or when you're putting a car together, it's usually the gaps between the fenders and the doors that you're looking at. You want them to be nice and aligned. You don't want them like a V gap or an A gap. You want them to be parallel, and you want everything to look nice, right? So this is just a fun example where I get to show you a little bit more of what I did. You would have a tolerance on the final assembly, right? That would be dictated by whoever dictates how they want things to look higher up in the organization. And then we have to spread that out between all the different parts and then make sure that the parts are actually meeting the spec. Okay, so that's a fun example, but what I really wanted to show you this because even though we're taking a difference, right, we're subtracting just like we were before, taking a subtraction, we have multiple things that vary. And so I want to show you where this formula comes from that we'll be using. So let me switch over to the next page. I'm actually just going to go all the way to the next page. Okay, get that lined up. Okay, so whether we're adding or subtracting variables, whatever operation we're doing, we have more variation than with just one thing, right? So sometimes it surprises people that even though we're subtracting, we're actually adding the variances. So when you have more than one thing that varies, it increases the variation, right? Now, there is this rule in statistics: if the variables are independent, then we can add the variances, okay? Now, we haven't used variance a lot in statistics. We mostly use the standard deviation. But the standard deviation squared is called the variance. Also, when you're calculating the standard deviation, it's the value before you take the square root. That's the variance, okay? So we use standard deviation more often in practical terms because it has the same units as the data. But there's this rule that the variances can be added if the variables are independent. Okay, so let's say part A and part B, they've got to be independent of each other in their measurements, right? Which they likely are because it's totally different parts, right? Okay, so if we're taking the variance of the difference, we can actually separate those out and take the variance of the first one plus the variance of the second one. Okay, and then you don't have to worry about this, but it's just if you're interested in how we get this formula down at the bottom here. The variance is, the standard deviation is when you take the square root. So then we would take the square root of that sum, okay? Or the variance is the standard deviation squared. So if I switch back to standard deviation, it'd be the standard deviation of the first one squared and the standard deviation of the second one squared. All in the square root. Okay, so that is the standard deviation, or in our case, we would be looking at standard error. Works for either one, just the interpretation is different. That's how you can see we're getting to our formula here. So this is our p hat 1 minus p hat 2, which is what we're trying to estimate. And as long as these conditions are met, which we'll go into the conditions next, just like you've seen before, as long as certain conditions are met, it follows a normal distribution. Okay, and the mean is the actual P1 minus P2, right? That's our mean. The mean stays the same. In this case, we're talking about the difference. And the standard error is, you can kind of see where it's coming from. It's the square root of a sum, and remember the PQ over N, right? But we had square root of PQ over N. So imagine we have the square root of the first one squared, because we had to square it. You can't just add things inside square roots, which it looks like that's what we're doing, but we're not. It would be the square root of this squared plus the square root of the second one squared, all in the square root, okay? So that's what we're doing if you're curious, or if you're like, just tell me the formula, I want to use it. That's what we're doing, right? So remember, it's the mean, comma, and then the standard error. Okay, so a little bit of fun on how we get this model. Now let's look at what conditions do we need and the actual formula, okay? Which you'll see looks similar, just with the hats on it. Okay, so confidence interval for two proportions, and this is called a z-estimate for a difference of proportions. A lot of these are going to look similar. Independence is the first condition. The individuals in each group and between groups, so that's the difference because we have two groups, must be independent of each other regarding the variable measured, okay, whatever the variable is we're measuring. Randomization, the data are from two independent random samples or two randomly assigned treatments. Okay, remember that random assignment is so important in an experiment because we want to make sure to spread out any other variables, right? We don't want it to be due to something else. Okay, so usually we'll have either one of those. Also have large population for each group, okay? So if sampling without replacement, the population must be 10 times the size of each group, okay? So you can see we really have the same conditions, it's just we're now doing it for each group. And what's my fourth color? Purple. The success failure condition for each group. Okay, so now remember when we actually get our data, we'll have the hats on it. So N hat, sorry, not N hat, N1 P hat 1, N1 Q hat 1 greater than or equal to 10, and N2 P hat 2 and N2 Q hat 2. So all four of those combinations greater than or equal to 10. The nice thing about this, if the data are given in a table, the 4 interior numbers are the successes and failures. So remember, this is the successes and failures for group 1, successes and failures expected for group 2. Those 4 interior numbers, I'll show you, are those 4 numbers. So that's really cool. I love that when that happens. We'll write those out in just a second. So now here's our formula. Just like you saw with the model, we take our point estimate, so p hat 1 minus p hat 2, plus or minus the critical z value, right, z star times the square root, times essentially z star times the standard error. And the standard error is our square root p hat 1 q hat 1 over n plus p hat 2 q hat 2 over n2. Okay, so remember this is our, well, this square root is our standard error, and the whole thing with the z star in it as well is the margin of error. Okay, and let me write point estimate. Point estimate is the general term. In this case, it's the difference of the 2 sample proportions. Okay, so hopefully this looks fairly familiar to you. It's different. It looks, it looks more daunting because there's a lot more symbols and it's longer. But it's the same thing we've been doing, which is the point estimate plus or minus z star times the standard error. Okay, now the z stars are actually the same. I'm going to move this up. The same that you're used to. Because we are using the normal distribution, and so that means we have those same critical z values. So I'll just show you real quick if you want a quick refresher. I've got my Staplet normal up here, so we would switch that to a value, and because we're using z, it's 0 for the mean and 1 for the standard error. And then we would do central of whatever our confidence level is. So let's do 0.95. I think that's the most familiar one, and that's the 1.96, right? So that's how we got those 4. And so you might need to find your own on a particular question, but a lot of times you'll be using these 4 that you can use your notes for. Okay, so different critical z values, right? That's how many standard errors we're going out for each confidence level. And then that's multiplied by the standard error. Okay, so let's go to the next page and let's write out the conditions for this. Problem, and then we'll use the formula as well, okay? I'm going to switch off of that page, but I'm going to refer to it for my conditions. Okay, so next we're going to write the conditions needed to find a theoretical, so remember conditions go with theoretical, confidence interval for the difference in the true proportions of kids who develop type 1 diabetes. PT minus PC, right? That's we're trying to estimate without the hats. Right, note the order is reversed so we can see what happens. So I did want to show you an example of what happens when we get the negative to negative, because we talked about that interpretation in the last video. So it doesn't really matter for the conditions, but when we use the formula in the next part, I'll show you how it's reversed so that you can see what to do in that case. Okay, so first of all, let's write out our conditions. So independence. Okay, so the kids in both groups, right? So all the kids, both groups and between groups must be independent in terms of the variable, right? So in this case, we're talking about in terms of their chance or risk of developing type 1 diabetes. Okay, so let's think about what we would want to consider, right? So genetics is probably a big factor in this. So we wouldn't want siblings or relatives, right? We would want to consider family history, other things like that. So let's just make a note of that. So no siblings, right? We definitely would not want identical twins. No siblings or family members. Consider family history, and then things like age, gender, race and ethnicity, the things we always consider. Maybe income, etc. Okay, so lots of things we need to consider to make sure that we are getting independence and can use this model. Okay, and then randomization. And I remember in reading the problem, the original statement, they said they did randomly assign kids to the two groups. Okay, so we have two randomly assigned groups. And since a lot of these are experiments, so like a before and after, or two different, actually not before and after, but because those would be the same subjects, but often two different groups. So comparing two different treatments, we need those to be randomly assigned. Okay, next one is large population. Okay, now this one's interesting because sometimes we have people coming from two different populations, and so we would want to specify those individually, right? But here we kind of have kids, they're both kids in the same population. The population of kids, or we might want to say high risk right, kids high at risk of developing this disease, which is what they're studying, must be at least 10 times 380, or sorry, 10 times 38, which is 380. Okay, now I'm not doubling it. It is written for each group. We just have two of those groups. And last, success, failure. We must have at least 10 successes. I'm going to put that in quotes. And 10 failures, in quotes, in our data. Because we are doing a confidence interval, remember all we have are our samples. So we're basing our conditions on our p-hats, right? So let me go back to the original problem here. Success is what we're measuring, right? Which in this case is not what we want, not what someone wants, which is developing diabetes. So success, that's why it's in quotes, is what we measure. So in this study, we had 26 kids develop in the control group and 16 in the treatment group. 12 did not in the control group and 22 did not. So these four interior numbers are the successes and failures. So that's really nice. We don't need to calculate them. We would get a decimal if we did, 38 times this fraction, well, you could see we get 26. But if we had gotten decimals, then we might come out close to these numbers, which is also fine. But I'm just going to use those 4 interior numbers, okay? So those numbers, I'm just going to draw a little box with those 4 squares, 26, 12, 16, and 22. Those are all greater than or equal to 10. So I'm going to check that off. I'll say all. All 4 are greater than or equal to 10. Okay. Now, this will be different when we do a hypothesis test, because in that case, we're assuming the null is true. And so we can't use the actual data. We have to use the null. Okay. But for this one, it's really nice. Okay. Let's do the formula. Use the formula to calculate, and then we're going to interpret the theoretical 95% confidence interval for the difference in the true proportion of kids who develop type 1 diabetes, PT minus PC, so teplizumab minus control. And then we're also going to check with the GeoGebra theoretical calculator. Okay. Great, so let's use the formula, but like I said before, it's reversed from the way we did it before, because I want to show you what happens when we do that, okay? All right, so I've got my formula nearby. I'm going to use this formula right here, but I'm going to put in the T's and C's, okay? Otherwise, I feel like I might get confused. So you're welcome to do that. You can always change the 1 and 2 to the letters of the problem. Okay, so P hat T minus P hat C plus or minus Z star. So I'm just going to write out the formula with the T's and C's first. Times the square root, big square root, P hat T Q hat T over N T plus P hat C Q hat C over N C. Okay. And for this one, because we're plugging these in a bunch of times, I do think it's useful to get the individual decimals. I didn't before when I did the difference. So let me just write that over on the side. So let me get a different color. P hat T was 16. That was the second one, 16 over 38. And let's get a decimal for that. 0.4211. And then P hat C was the 26 over 38. 0.6842. And then let me go ahead and subtract those two. And at this point, it's okay either way to either do the entire subtraction like I showed you before, or to subtract these two decimals, okay? There's going to be a little bit of leeway for decimal places. So 0.4211, oops, that's not right. 4211 minus 0.6842. Okay, so you can see it comes out very close, but there is a tiny bit of round off error because we ended up with 3.2 the last time, and this is 3.1. Okay. So I'm going to write negative 0.2631 plus or minus, so that's the difference I just got. Plus or minus our Z star. So we are using the 95% confidence level. So that's our 1.96 times the square root. I'm going to try to squeeze it in here before this little box. This is where I've got to put in all my decimals, right? So 0.4211 times 1 minus 4211 over 38. Plus, okay, I'm going to go a little bit past this box here. 0.6842, 1 minus 0.6842. all over 38. Okay, hopefully you can see that okay. Okay, now this is where I would strongly recommend the Desmos online calculator, right? We can do this on here, but it's going to be harder to find a mistake if we have a typo or something. So I'm going to write my difference, negative 0.2631 plus or minus. Just like before, I want to do the whole margin of error at one time because I don't want additional round off error from what I've already got. So I'm going to go over to Desmos. And this is a perfect time to use Desmos because you can see everything at once, right? So I'm going to put in the 1.96 times the square root of 0.4211 parentheses 1 minus 0.4211 close parentheses, and notice how I'm still in the square root over 38. Now to get over, I'm going to use the right arrow because I want to stay in the square root and do a plus. Oops, even though I wrote equal, do a plus. Now I can do 0.6842 parentheses 1 minus 0.6842 close parenthesis divide by 38. Okay, let's just proofread this whole thing. So 1.96, 0.4211, 1 minus the same thing over 38, 0.6842, 1 minus the whole thing over 38. Okay, great. And so this gives us our margin of error over on the right, 0.2156. Okay, I wrote that down, 0.2156, yep, checked rounding. Okay, 0.2156. Great, so that's our margin of error. Now we can do the subtraction, right? The addition and subtraction part. Now you can do that either, you can stick with Desmos and do it, or do it on a regular calculator. I'm just going to stick with Desmos since I have it here. Just gotta click on there. Okay, enter gets me down below that. So negative, remember put your negative in there, 0.2631 minus 0.2156. Okay, so that gives me the negative one. Negative 0.2631 plus, actually I don't know if this is gonna be positive or negative. 0.2156. Right, okay. These were supposed to both be negative because they were both positive in the other, when we did it in the other order. Okay, so let me write this down and I'll switch back to the notes. So negative 0.4787, comma, negative 0.0475. Okay. Great, so this is what we got. We got negative to negative, right? So, and remember our subtraction. If the second one, you can think of the negative one, the second one is bigger, that means we'll get a negative, right? So again, the control group is bigger. We've just switched the order. Okay, so, but we don't want to write these negative percentages. That doesn't make any sense, right? So let me show you how we're going to write out our interpretation. And then we'll compare it with what we got before. Let me move this up just so I don't have to move it again, hopefully. Okay, we can be 95% confident that the true proportion of kids who will develop diabetes, so same exact way before, is notice how when you have two negatives that the order is reversed, right? So more negative is a bigger value and less negative is a smaller value. So that's why I'm going to reverse the order. So I'm going to start with 4.75. 4.75% to, then I'm going to go to 47.87% lower this time. I'm going to be 95% confident that the true proportion of kids who will develop diabetes or type 1 diabetes is 4.75 to 47.87% lower with the drug teplizumab than without it. Okay, so this time by putting the treatment first, then we're putting that one first and it's lower. Okay, interesting, huh? So same result, just doing it in the other order. Now let me find my page again just to double check. Before we got, and it was with bootstrapping, right? So this was the 95%, it was 5.3 to 47.4, but very close, right? Same ballpark. Okay. All right, great. So that last thing is checking with the GeoGebra theoretical calculator. So I've got a screenshot here, but I'm going to show you, actually go through it. So GeoGebra Classic, remember it starts with the distribution tab over here. We click on statistics. Now we need to look for the test, or actually the interval we're doing, which is Z estimate, difference of proportions. Okay. Confidence level, enter that in, then we have a place to put in our successes and failures. Okay, so we've got 26, I'm going to keep the same order I just did, out of 38. Sorry, that would be 16. I was looking at the way we did it before. 16 out of 38, 26 out of 38 is the second one. And you can tell by the way if it comes up positive or negative. So the difference came out negative, plus or minus 0.2156. So that is, oh, it got the 2 before, so it's doing the more exact fractions. But it's very, very close. And you can see it has the margin of error right there, plus or minus, and it has the 2 bounds, which are just off by 1. Okay, if we reverse the order, we would get the positive, just the positive result with those in the other order. Okay, so you have a screenshot of that. Z estimate difference of proportions. Remember, this is the statistics tab, and this is our p hat t, and this is our p hat c. What else do I want to highlight on here? Then they kind of repeat the p hats again. This is our margin of error right there, and this is our lower bound and upper bound. Okay. Okay, so always good to check, but of course you're going to need to show your work to with these formulas. So be sure to practice that. But then also, if it's not coming out right, check this. And if if something's not coming out right, then check, proofread everything on your Desmos calculator like this. Okay. Okay, great. Thanks for watching, and I'll see you in the next video.